Another draft science, mostly physics, video. Yes. Anyway. Alright, so response to, yes, the liar. Anyway, just we're going over this math crap again. And, so, you know, he had to push the envelope by doing the galactic, velocity, which is, in my opinion, just points out how broken physics is, that they could even believe the sun is moving that fast through the galaxy. Because in my opinion, the only way it could be doing that and staying where it is there'd have to be incredible gravity from the galaxy or something that's making it move that fast. And if there's a gravity that strong, it would be pulling Pluto right the hell out of its orbit. I mean, if the sun can be going 143 miles a second through the galaxy, Pluto's lost. Because it's going to say, hey, the gravity from the galaxy is a lot stronger than the gravity from the sun. So, see ya, I'm heading. And even the Earth would be pulled away. The gravity from the sun is tiny, where the Earth is compared to a force capable of moving the sun, this kind of velocity. So clearly they don't know. Galaxies are really slow places. They're not fast places at all. As you get bigger, everything goes really slow. So I would argue that I don't think you could put a solar system, keep it in shape, especially with weakly held planets that take 100 years to make an orbit, that they wouldn't be held in their orbits. And you'd certainly have an indication of a gross eccentricity. I mean, their orbit would be bent in a way that would be kind of obvious that they're being pulled by the galactic power. And no one's talked about planets being pulled by the galaxy. So I just think that's a silly number. And so, yeah, I'm not going to pay much attention to that one. So anyway, getting back to the realistic numbers. So the quandary we're arguing. See, I'm arguing that light is constant, straight, and it never does anything variant. Okay, once it's emitted, once a photon is released, it does one thing. It goes in a straight line at the speed of light, and it just doesn't do anything else. So you can either admit it crooked or something, but you can't bend it. It won't go anywhere but straight. Their theory sort of is light will compensate for some kind of velocity thing, depending on the circumstance. I don't know exactly what their argument is, frankly, because it breaks the fundamental point. That, here's your basic chart. Here's the speed of light. Now, if I add anything at all, any momentum in any other direction, but the direction that the speed of light's going, anything, you end up with a hypotenuse. And this hypotenuse will always be longer than this speed of light line. So this will be your new speed of light. So unless they want to say this is the speed of light, but then it would be variant based on how fast you went. So if you went very slow, it would be a different speed, the sideways motion. So depending on how fast I move a laser pointer will decide how fast the speed of light is that leaves. And that doesn't make any sense. So there is a real question here to be answered. So what I'm basically arguing is that when the emitter of light is moving, it will release light as it's moving. And if the receiver is moving the same speed as the emitter, well, the light can't get to that first spot in time. So that's going to be a null. And so at some point over from that spot is where all of these times this speed will now pick up all of them at the same location. So all of this will end up here, because this will just move as these catch up. So this one was first. It lands a little bit off of that perpendicular, and the rest of them show up at just the right time behind to end up hitting that same spot. That's my theory of light. And so the end result is there'll be some deflection off perfectly perpendicular where the light will end up going. Probably should have drew it the other way, because I'm saying the light's obviously it can't hit perpendicular because the first bit of perpendicular gets out of the way. The target moves and it hits right behind the perpendicular. So if this was perpendicular here, it hits behind perpendicular, that kind of thing. Alright. So that's sort of the argument. It's kind of a fundamental question, because if they're right, then when we look at Saturn with a telescope, we're seeing exactly where Saturn is because the light moved with Saturn. It's carrying its velocity. And so it bent to get to us, in the future. It made it because it anticipated where we were going to be. And I think we know that's not true. So problem one there. But I think in lots of examples we can find the problem. But obviously this also creates a problem in the sense that, well, if there's a huge amount of variance, then all the buildings are a little bit crooked and everything's a little bit off because no one's accounting for the fact that the laser's a little different depending on what time of year you're pointing it. But that made me think that, there's kind of a famous giant pendulum. I think it's in that museum in Washington, whatever it's called, Smithsonian or something. But it's just basically a giant pendulum and hangs down, has a little lump on the bottom, and it has all these little soldiers they put up, and it just knocks them over, as the year goes on. It just blah 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 blah, just plows them over. So at different times of the year, plumb is really a different line. So all these surveyors who are using a plumb bob, they really should be figuring for the time of the year, because at different time of the year the plumb bob's going to be a little different plumb. Plumb ain't going to be plumb. But I guess for most of their calculations it's close enough, so it doesn't matter. Approximation is good enough. And most lasers are just doing things that are a few meters, a few hundred meters at the very most. And so a little bit tiny off at the 100 meters, well, that ain't so big a deal. That's part of this. That's built into this thing. Now another problem I thought of that it's sort of irritating, is the divergence of lasers. Because that's still a problem. Like, why do they diverge in the first place? And part of the problem is that they're moving. They have velocity. So they're broken. And so they can't create parallel rays of light because their guts are moving. And so this divergence might be hidden inside of the divergence of the beam. So as the beam is getting bigger, it's really hiding the fact that the beam is off in the opposite way. It's in the fog of the offness. And it doesn't matter which way your velocity is going anymore, because at any velocity it creates the same divergence. It's not specific. It's the same kind of broken. The broken just ends up being a scatter. So any velocity starts creating scatter. So I was thinking a way around that might be to take a slow motion film of a laser beam and see if you can detect any where it's doing this off a little bit different, off in different ways at some kind of cycle. And that might tell you something about what's going on inside the laser, and that the offness might have a cycle to it. And that's why any velocity is creating a problem, because any velocity creates the cycle. And the faster the velocity, the faster the cycling. But you'll never be able to figure out, because it's a round wheel. The cycle inside the matter is a round wheel. You'll never be able to tell directionality because it just spins the wheel quicker depending on the velocity. It doesn't care which direction it's in. So you're always stuck with a broken emitter. So that might just negate this whole conversation. And I hate to negate it before we get started, but it would have to be calculated that if the way you detect this error in the direction of the laser has to somehow be related to some kind of light that's truly coherent. Because if it is diverging, you know, then you're in trouble. So that would be the real thing to seek, is a laser that's less and less divergent. And then you get shorter distances. Shorter distances require closer measurements, so you're still fucked. So, might not be able to answer the question with lasers, which really is just a disappointing idea. So there might be some other way to acquire a single photon experiment, for example. But then we're back to the Heisenberg problem, where we can't admit a single photon and know where it's going. So we have to, I would think if you put a tiny hole, and a tiny hole, and a tiny, like I said, if you had like 6 different layers, well, then the last layer is still going to make it go crooked. But you'd almost argue, how could it get through the first 3 layers if the last layer is going to make it go crooked? I mean, theoretically, if you took a plate, like 10 plates, and you had just a tiny pinhole in each plate, exactly lined up, if a photon made it through 9 of them without diffracting, it should be able to get through the 10th one without diffracting. One could figure. And so that might be a pretty straight photon. I mean, it might be moving pretty straight right through the middle of all those holes, because it never diffracted, never bent enough to fuck it up. So maybe it would require that kind of light. And that's a very much more complicated experiment to catch one photon. Single photon emissions at hundreds of feet. That's, you know, that's laboratories, government funding kind of an experiment. So anyway, like I said, I'm a little disappointed that I thought of that stinking lousy circumstance. Like I said, like maybe the divergence of light is a symptom of galactic velocity and Earth velocity and Sun velocity, and all these added up velocities are what's making the light diverge in the first place. So that might be just an interesting experiment, just to see if you can create more erraticacy in a laser by moving it all over the place, and see if you can actually screw it up more, make it diverge more, make the beam more divergent by moving the emitter. And I guess if you find out that's true, I suppose you could put it like on a high-speed sled or something. Well, there has to be some way you can take a photograph, you know, a really sharp image of the exact laser light. But I mean, that might be, well, it's automatically going to look like it's diverging, at least in the direction you're moving, unless you have you have to have a high-speed camera. But yeah, you should. It seems to me that there might be some way to measure that. All right. Well, anyway, whatever. It's just irritating, because this would be a great question to be able to answer. I think it's answered by the math itself, in the sense you can't add velocity to light without changing its speed. It's just a fact. Another catch I was going to throw in, just as a thought, is you also have to account for the tiny bit of acceleration that the Earth, say if you were to release the Earth, its velocity wouldn't be truly its velocity, because it would still have the last bit of velocity that was caused by the acceleration towards the Sun. So if the Sun instantly blew up, there would still be the last little bit of push it got from the Sun's gravity, and that little push increased its velocity. So its true velocity is a little bit slower, and it's adding that extra velocity. So its orbital velocity will be the same, theoretically, almost the same, as its release velocity, because you always added that last bit. That last bit did actually bend it and did actually give it more velocity. So you can never really escape the last bit of velocity you got when you last got bent. And so the true velocity actually going in the direction would be a little different than the actual velocity it would leave at. But I don't think it'd be significant enough to screw any of this math up. Alright, so anyway, the math. So yeah, I don't know why he bothered with the galactic thing, because that just gets into bullshit numbers in my opinion. Doing the yearly thing is a nice idea, you know, because it's a nice big number. But yeah, I mean, who's going to be able to create a stable enough experiment to do that? So, you know, I was sort of stuck with the day thing, and those are the numbers I was coming up with, and those are kind of a long number. You got to go a, you know, a long way. My final answer is let's see, 10 miles. Yeah, so 10 miles per an inch. Yeah, so do the math. You know, you can go down to, you know, that's if we just do the seeing it on one side. See, at least I see he was doing the math based on just one movement. So if you take both movements into account, you know, first 1,000 miles one way and 1,000 miles the other way, then you can double this. So then you end up with 1 inch is 5 miles, and that's 1 inch on both sides. I mean, divided over both sides. So it'll be a, you know, ½ inch one way and then a ½ inch the other way. You know. But anyway, yeah. So you're still stuck with my kind of like, you know, a mile. You're going to get like just 4 millimeters to play with. So it does get a little bit tricky. Well, I think that's at 2 miles. But anyway, yeah, it would require kind of a serious experiment. But I'm going to try some unserious experiments here just to see if there is a difference in what a laser looks like at different geographic pointing locations, and see if there's any obvious difference in how the emitter emits at those different orientations. So anyway, the thing that was funny was, okay, so I did the math, like I averaged, I cut the speed of light down to 180,000 miles a second instead of 183, I think it is, right? Something like that. And then I divided it by, well, anyway, I was doing the conversion to getting them both into miles per second. Well, anyway, and this is just such a great number. So this is like, I think, feet or something. Well, anyway, look at this number, 6666666. So that was the proportion. So the proportion of, you know, from what I'm looking, the unit, 1 unit would be to this number, 666,666.6666666, and then a 7. I just thought that was just so perfect. Just so funny that it's evil, but only to a point. You know, it's not infinitely evil. It stops the evil. But it just seems, you know, it just seemed very funny. You know, that it came out that way. When I was just trying to get the two things into the same units, and that's what you end up with, is a unit number. So if you average, if you just cut the, if you just make the speed of the rotation of the Earth 1,000 miles, which is, again, not the truth exactly, and then you make the speed of light 180,000, that's what you end up with, and I just think that's very funny. But anyway, that's a coincidence. I just think it's a little bit funny. Alright, is there anything else I got to say on this? Maybe I'll do some deGrasse Tyson stuff, because I don't know if there's anything else to report. But I think it's important. It's important. I just don't know how you can account for this idea of light having momentum first as a physics question. I think it's just bad physics to give one force these attributes that none of the other forces have, the stuff moving the speed of light. And it's also nonsensical in the sense that, well, I mean, if you can move the stuff sideways, why can't you move it faster and slower? It just creates so many problems. And I just think everything needs to be understood as just a force. I mean, the simple absolute question, you know, instead of E equals mc squared, the real game is going to be F equals everything. Everything's just force. There's nothing else. It's all force. Anyway, and you can't, force can't affect forces. You know, I mean, if Newton knew that, he would have made a better equation. It wouldn't have been m1 plus m2. It would have been, first you have to do the gravity for this object, and then you do the gravity for that object, and then you can combine. But you can't do them together. That's cheating. Alright, so, yeah, I guess we'll do some of this Degrassi-Tyson crap. Well, maybe I just leave this as a separate video. This is one subject, at least. So let's see if there's anything else that has to be said on it. Again, I would just argue that this galactic number is just silly. And, you know, I think it's, again, their problem is they're not understanding redshift. So I'll make my argument for redshift again, is that anything that's moving in towards us, so towards perpendicular to our line of sight, so we're looking out this way, and to the universe, or to anything actually, trains, it doesn't matter, but it'd have to go fast enough for us to see the redshift. The point is the light that we're going to see, that's going to reflect off of it, is clearly going to have to be angled at us for us to see it, or it's going to have to do this, you know, get to us eventually thing. But the point is the emitter is moving in this direction, and the emitter is going to be gaining on its distribution. So my point is that emitters are basically just dropping, okay, light. They're just dropping it like they're in a car. Alright, now if you were in a car and you drop something that moves a lot faster than you, it leaves instantaneously almost from your perception, you could sort of understand that if I'm moving this way and I drop it, I'm dropping it from a forward location the next time I drop it. So it goes even, you know what I'm saying, it's not that it's catching up on the previous one, but it's obviously, if it had a frequency, that frequency would now be compressed, because I keep dropping it from a different location. So any frequency is going to get compressed coming this way, so it's going to look blue. Everything's going to look a lot closer together than it actually is, because I'm dropping them further into space each time. And if I'm doing the opposite, I'm dropping them out the back, well, you can sort of understand that as I move away, I'm increasing the frequency now. Because each time I drop one, I've moved away, further away. So now the frequency is going to, you know, get wider and wider and wider, and that would be your redshift. Well, the same thing's happening when you're moving this way and this way. When you're moving in and out of the frame, you're doing the same thing. You're just not doing it as dramatically. You're still pushing light, and the push is not unreal. Let me see how to say that more precisely or accurately. In terms of the effect on frequency, because now you're dropping light out this way, but you're still dropping it at different locations each time, and those locations will add up to a frequency change. Now, the math is kind of like this math. You won't get a one-to-one relationship to the frequency change, just as you do with forward and back. I mean, forward and back, you get an obvious change in the compression of the frequency. This will be a less obvious compression, but it's going to be if the speed is anything substantial, it's going to be not insignificant. It would be 1/2 of what it would be if it was pointed at you, let's say. But it's going to have a shifting effect on the light. And especially you can see it when it's going in the opposite direction. You can kind of get the idea that you know, whatever you're seeing light from where it is at the time, and the time like I said, each time it's re-emitting light. It's not reflecting light. It's absorbing it and re-emitting it. So it's still an emitter moving away from you. It's just not moving away from you as fast as if it was going this way away from you, but it's still away. This line is still an away line. So when they see redshift, the physicist people, the real smart people, aren't realizing that this motion is also causing shift, and you have to combine all the motions to understand what's really happening, because they're going to be combined in what you're going to see. If it's receding away from you, which is causing redshift, but at the same time it's coming at you. So it's going this way away, but it's moving that way towards your center. Then it's going to be a combination of redshift and blue shift, and it's going to be some n number that isn't going to really reflect where it's going, which is at a diagonal. And that diagonal is important because part of that diagonal is direction towards you. So you're going to think its velocity is very slow when actually its velocity is very fast. You're just not realizing that its velocity is slower because part of its redshift has gotten eaten up by the blue shift towards us. Or in the more likely case, the redshift away from us is combining with a redshift going this way. So they think the thing is going really fast away from us when it's really doing two things. It's going sideways, which again, when you combine two speeds, you don't get that speed plus that speed. You get something that's just a hypotenuse. Okay, your end product isn't. You don't get to when a three-dimensional thing is moving in two planes at once. You're not allowed to just add up the two speeds and say, well, if I'm going half the speed of light this way and half the speed of light this way, I'm going the speed of light that way. It doesn't add up that way. All you get is a statistical combination of the two. You get this hypotenuse, okay, which isn't, which is bigger, but it's only like 28% bigger or something if this is half the speed of light. Something like that. So anyway, yeah. Alright, so is there anything else on this subject? It's an interesting subject and gets into this whole redshift thing and why the numbers of how fast stuff is moving in the galactically is so wrong. But I mean, they should have figured out these numbers can't be right just from the fact that these numbers would indicate a strength of gravity so strong that the gravity from the galaxy on Pluto would be stronger than the gravity from the sun on Pluto, and Pluto would go galactic. Okay, anyway, I think that's enough for this video. So, comments welcome. Some asshole, I'll point it out in this video because it's sort of a junk video. Well, junkier. I hate these cunts. It's, they make these insinuations. Where are you hiding gapped mines? What does that even mean? I mean, I'm assuming he's saying, why am I hiding? But I don't know. I don't know who gapped mines is. Where are you hiding gapped mines? How am I supposed to know what that means? And then how do I explain quarks? Well, I already explained what I would argue if you're going to say quarks or something. Actually, we've never seen a quark outside of a cloud chamber. And we haven't even seen them in a cloud chamber in the sense that all we saw was what we're consuming are byproducts of quark behavior. But I've already argued that if electrons are made of something, they're made of strings of polarization. And those strings of polarization are probably what the quarks are. But whatever. Clumps of connected polarized clumps. Damn. But yeah, I just wanted to point out that I think it's here somewhere. Go on, mouse, you can work. I saw you work before. I know you can do it. You did it before. I had the I had my stupid analytical thingy opened. Well, I'll just do it here. I think I can do it here. Community settings. Yeah, that should do it. Look, these are the assholes I have blocked. So if anybody wants me to unblock one of these assholes, then just vouch for him and say, as soon as he's a rude, obnoxious cunt, I can block you too. Because that's all these are just complete. I mean, I haven't blocked anybody who's making valid arguments. I just block people like Secret Half Jew and, people with non-existent screen names. Which is down here now. Why have these moved? I haven't changed this in like 2 weeks. I haven't blocked anybody. Why are they in a different order? That is really strange. Anyway, these are just assholes who can't make arguments. All they can do is make insults. And they're too pussy to make videos. See, now if they made videos and I could play their video and mock them for the stupidity and how dumb they are, like I can mock Piro for being a dumbass and a liar, and I can mock Hathaway for being a dumbass and a liar, that's different. But these pussies don't put up. They just think they have a right to come in my living room, take a shit, and they won't give me a living room to shit in. You know, they don't have one. They're sitting in some homeless shelter, or they're sitting in a cardboard box in an alley somewhere. Well, frankly, I don't win shitting in a cardboard box in an alley. So until they have some good place for me to shit, like right on top of their head, fuck them. That's my philosophy. You don't think that's fair? Fuck you, cunt. I mean, I don't go on other people's videos and type rude shit. I don't do it. So I'm not being a hypocrite here. Cunts. These assholes come to me. I don't go looking for them to say, oh, your life is a piece of shit and you're a sucky, bald-headed, motherfucking, micro-dick, penis, fucker, bastard. I don't bother doing that. They bring it here. And then they don't have the balls to allow me to shit on their head in return, to do them the same kind of favor. Pussy shit. Anyway. Alright, so that's enough. Probably. Yeah. So yeah, I haven't gotten an answer from, the Theora guy hasn't done the, why little dots on mirrors and telescopes. You know, why do we have big mirrors if all we're looking at is a little dot? Yeah, so his answer, we haven't gotten his answer yet. Anyway, so anyway, till next time. Such, I don't think we have. I guess I could check, see if we've got an answer yet. He does these dopey, like, completely unscientific experiments, you know, not head-to-head comparison. Look how fast this opens where I put a magnet under it. Yeah, well, no, it's not compared to one where I don't put a magnet under it. No, no, I don't do those kind of experiments. No controlled experiments here. No, 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 no. This one was a little bit interesting because he did this clockwise thing, you know. I mean, it was actually counterclockwise. And then he flipped the magnet over, and it was counterclockwise. I don't know, it's like almost like, well, what are you proving there? It seems like it went counterclockwise both times, which probably has something to do with the physics, you know, of you know, how the stuff is, when you're releasing it, the stuff is breaking down, and it breaks down in the same way that toilet water spins in a toilet or something. It's totally not evidence of anything. Alright, so no, we don't have anything new here, right? I think I reloaded the page. Oh, there we go, some new stuff. Pro tip, user missing out IR pass filter, Fuji. Let's see, favorite beloved, you know, the $10,000 camera, nuts. Sorry. He's a really hilarious guy, right? Because he spends money like, you know, he's got $1 million in the bank that just keeps growing and growing and growing, and he could just spend millions of dollars every year, no problem. And yet he claims he's poor and he, you know, barely can scrape by. It's just hilarious, but he has like $6 million, maybe $20 million worth of gear. I mean, anyway, it's, you know, it's incomprehensibly not the real story. Yeah, there's some other. The reality is not. You know, this is the theory of relativity. I can make up my own story in my own frame. And it doesn't have anything to do with your reality. You know. Okay, anyway, enough. So I think that's enough for this video. So till next time and such. See if Piro made another video. Really was a horrible. I mean, he just kind of dragged the whole thing out in an insanely silly way by first not having his microphone on, and then there was some other bullshit, and then there was some other bullshit. Sound fixed at 2 minutes. Oh, okay, so he at least put it in the title. So anyway, I don't know what Owen McDonald is. Well, maybe he's Mike Donald. Owen Mike Donald, or Ma Conald. Yeah. Anyway. enough. I'm sorry. Longer than it should have been.